Hey guys, so in this video, I'll be talking about power series. So if you remember during our last meeting, the last couple of examples that we did, I mentioned that they are actually power series. So here, what we're gonna do is we state the formal definition of power series and some more terminologies. And then later, we will also consider some power series representing some functions. So let's get started. So here we define a series of the form sum from n equals 0 to infinity of Cn x minus a to the power n. If we expand this is c sub 0 plus c sub 1 times x minus 1 plus c sub 2 times x minus 2 squared plus so on and so forth, where x is a variable and a is a fixed real number and cn's are constants, is called a power series centered at a or power series about a. Okay, so in here we are summing from n equals 0 to plus infinity. So a quick observation, when n equals 0, we got c sub 0 x minus a to the power 0. This part here, we will just treat this as 1, even if your x is equal to a. Take note, 0 to the 0, for us, this is undefined. So, in the definition of power series, when n equals 0, we have c sub 0 times x minus a to the power 0, or simply we just write this as c sub 0. That's what we see in here. And of course, we got c sub 1 times x minus a, n equals 1, plus c sub 2 times x minus a squared, that's n equals 2, and then so on and so forth. So this is the formal definition of a power series about a or centered at a. So here we adopt the convention that x minus a to the power 0, that's equal to 1, even when x is equal to a. Some examples of power series, we have sum x to the power n running from 0 to plus infinity. This is 1 plus x squared plus x cubed plus so on and so forth. And this is a power series centered at 0. So notice you don't see an a. This is actually x minus 0 to the power n. And then you got the sum n from 0 to plus infinity. And of course, if you have your c sub n, the c sub n is equal to 1 for all n. So indeed, this is a power series centered at 0. Then another power series here, we have the sum from n equals 0 to plus infinity of x minus 1 to the power n divided by n factorial. So if we expand this, when n equals 1, we have 1 over 1 factorial, but 1 factorial is equal to 1. When n equals 0, we have 1 over 0 factorial, but 0 factorial, we define this to be equal to 1. That's why you see 1 in here. And then, of course, we have 1 over 1 factorial, which is also equal to 1. So you notice that the coefficient of x minus 1 here is equal to 1. And then when n equals 2, you got the 2 factorial here, that's squared. When n equals 3, this is 3 factorial here, this is cube, and so on and so forth. So this is a power series centered at 1. Okay? Now, the natural question is, just like what we did in the last meeting, when does a power series converge? So I already mentioned the techniques and the steps that we're going to do and what we're going to use in order to determine the values of x for which this power series or the given power series converge. So let us consider the following. If x, so we have the power series here, is Cn x minus a to the power n from 0 to plus infinity. If x is equal to a, then this power series becomes, so we have some Cn x minus a to the n from 0 to plus infinity. When x equals a, this becomes c sub 0. Again, take note, we adopt the convention that x minus a to the power 0, this is equal to 1, even if your x is equal to a. So, if x equals a, this here, if you expand this, everything will be 0 except for this c sub 0. Okay? Let us try the expansion. Let us write the expansion here. C sub 0 plus C sub 1 x minus a plus C sub 2 plus C sub 2 x minus a squared plus so on and so forth. So when x equals a, all of this will be 0, including the others here, and we will be left with C sub 0. So in this case, x equals a is always a point of convergence of a power series. Okay? Now, when we did the first example that that is of the form of a power series in our last meeting, we found that our power series back then converge on a certain interval. So, we can include this possibility. Power series can converge on a certain interval. And our last example, we found that the power series converges everywhere. Like whatever x you choose, the power series will converge. So we have actually these three possibilities. The power series can only converge possibly at x equals a, or the power series converges on a certain interval, or the power series converges everywhere. So we summarize that to a single theorem. Given a power series, which is given by this one, there are only three possibilities. The first one, the series converge only at x equals a. That is the first case that we saw earlier. Second case is that the power series converges for all real numbers x, or all real values of x. And lastly, we can find a positive number r. Okay? We can find a positive number r such that the series converges if the absolute value of x minus a is less than r, and diverges if the absolute value of x minus a is greater than r. Okay? So again, we are given a power series. Then there will be only three possibilities. The series converge only at x equals a, the series converges for all real numbers of x, or that the series converges inside an interval and diverges outside that interval. Now, take note, there is a case when the absolute value of x minus a is equal to r. In this case, we don't know yet if the power series converges for these possibilities. If we look at this is x minus a equals plus minus r, or that x is equal to a plus and minus r. So if we look at that on the interval, this is your a, this one here, this is of length r. This particular point here, this is your a plus r, and this particular point here, this is your a minus r. A minus r. So basically, when the absolute value is equal to r, we are actually looking at the endpoints of our interval. And like I said, we don't know yet if the power series converges there or diverges there. So we will need to check the convergence or divergence at those endpoints. Now, for the first case, we define r equals 0. For the second case, we define r equals infinity. And we call this r here, the radius of convergence of the power series. Radius of convergence of the power series. So if we look at the interval, if the convergence is only at a, well, the radius is equal to 0 because it is only at this point. On the other hand, if we have the second case, the series converges for all real number. But that involves all the real numbers. So the radius is equal to plus infinity. The third case, well, it is a positive number. So if we go back here, this r here, that's actually the radius. It is the distance from A. So the power series is convergent for all x's that are within this r radius from A. Okay? So we call that the radius of convergence. And then the set of all values of x for which the series converges, we call it the interval of convergence of the power series. Okay? So let us consider some examples here. Determine the radius of convergence and the interval of convergence of the power series, this one here. Okay, so we have the sum from n equals 0 to plus infinity of n factorial x minus 1 to the power n. Now, if we expand this, we will have 1 plus x minus 1 plus 2 factorial x minus 1 squared plus 3 factorial x minus 1 cubed plus so on and so forth. So like what we mentioned earlier, this is always convergent at x equals 1. So always convergent at x equals 1. It's just what? The power series and factorial, and from 0 to plus infinity, x minus 1 to the n, this is just 1. But what about when x is not equal to 1? Like what we did in our last meeting, we just calculate limit as n approaches infinity of a sub n plus 1 over a sub n in the absolute values. But this is equal to the limit as n approaches infinity of n plus 1 factorial x minus a, x minus 1 to the n plus 1 divided by n factorial x minus 1 to the n, and this is in absolute values. But this simplifies into limit as n approaches infinity of n plus 1 times the absolute value of x minus 1 to the power 1. Correct? Take note, this one, you can write this as x minus 1 to the n x minus 1, while this one, you can write this as n plus 1 times n factorial. So, n factorial, you can cancel it. X minus 1 to the n, you can cancel it, and we will be left with n plus 1 times absolute value of x minus 1. But since your x is not equal to 1, this is not equal to 0. This is a number. But as n approaches infinity, this will go to plus infinity. Right? Again, this is not equal to 0. As n approaches infinity, this will go to infinity. So the limit is equal to infinity. And this is well above 1. So by ratio test, this series will diverge when x not equal to 1. Okay? By ratio test, the series diverges when x not equal to 1. Which means this one is only convergent when x equals 1. So the radius of convergence, just to finish, so r, it is equal to 0, and we call this radius, and interval of convergence this is just 1. IOC, interval of convergence. Although this is not an interval, but let's just say it is an interval of the interval of convergence. So this completes the solution to our problem. So again, it's similar to what we did during our last meeting. It's just that now we have terminologies to use. Next problem. I think this one we did this in our last meeting, but let us show it again. We have n equals 0 to plus infinity x to the n over n factorial. This is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus so on and so forth. We can skip when the first step, when x equals 0, we can always skip that. So let us move to the second part for x not equal to 0. We want to find the limit as n approaches plus infinity, a n plus 1 over a n in absolute values. This is equal to the limit as n approaches infinity of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. But this simplifies to limit as n approaches infinity of absolute value of x divided by n plus 1. And the limit here, this is equal to 0, which is always less than 1. So, by ratio test, we have here that the series is convergent for any x. For any x. Which means the radius of convergence, this is equal to plus infinity. And of course, the interval of convergence, this is from negative infinity to plus infinity, or you can write the symbol for the set of real numbers. Okay? So in the previous example, we got the first case. In this example, we got the second case. Now let us look at this one. So here, well, let us expand this. Take note, it starts with n equals 1 because you have a denominator n. In here, it started n equals 0 even though you have the denominator n there, but it's n factorial. Okay, and 0 factorial is equal to 1. Here, you are forced to start with n equals 1. Which means this here, if we expand, we will have x plus x squared over 2 plus x cubed over 3 plus so on and so forth. So let us answer this one. For x not equal to 0, we get the limit as n approaches infinity of a n plus 1 over a n. This is equal to the limit as n approaches infinity of x to the n plus 1 divided by n plus 1 times n over x to the n. This one here, we have the limit as n approaches infinity of absolute value of x times n over n plus 1. So in here, notice that we can only cancel x to the n. And this one, well, it remains n over n plus 1. But as n approaches infinity, this expression is going to 1. So here, we will have the absolute value of x. Now remember, if we want this to be convergent, if we want the power series to be convergent, we want this to be less than 1. We need this. So need. So the power series is convergent. But this one, it means that, well, absolute value, so absolute value of x less than 1 implies we got -1 less than x less than 1. And this means that the radius is equal to 1. This is what we see. Now, a lot of students are confused with how to obtain the radius. When you are in the third case, you have to make sure that you have written it in the form x minus a in absolute value less than some number. And that number will become r. Now, there will be times that maybe your expression becomes x minus a minus 2 in absolute value over 3 less than 1. Notice here we only have the absolute value of x minus a. So you have to isolate the absolute value of x minus 2. In this case, you will be able to write absolute value of x minus 2. If you multiply 3 on both sides, that absolute value will be less than 3. And this becomes your r for this case. Okay? So again, what I'm saying is you have to isolate the absolute value of x minus a. And on the other side of your inequality, that becomes your r. Here, absolute value of x minus 2 is not isolated. It has denominator 3. In this particular example, well, you only have this absolute value of x. There's no denominator. Well, the denominator is equal to 1, whatever. So that means this is now our r. So we now have the radius of convergence. We are sure that the power series is convergent between -1 and 1, excluding those endpoints. So we now know that the power series is convergent in the interval -1 to 1. What about at x equals 1 and at x equals -1. In this case, we check. So if we check that for x equals 1, we have the power series 1 over n, and from 1 up to plus infinity, this is divergent. This is the harmonic power series or harmonic series. On the other hand, when x equals -1, we have the series n from 1 up to plus infinity of -1 to the n over n. And this is convergent, alternating harmonic series. Alternating harmonic series. So you can use those previous examples that we have already shown, unless it is the thing that you need to show. So in this case, we already did this particular series. We can just bring our previous example. But anyway, so what does this mean? The power series is convergent in the interval -1 to 1, excluding -1 and 1. But we also found out that your power series is divergent when x equals 1, but convergent when x equals -1. So finally, the interval of convergence, this will be -1 to 1, closed at -1, but open at +1. Okay? Now, take note, this does not violate our theorem. Let us go back to the theorem. This does not violate this theorem. It only says converges if strictly less than, diverges if strictly greater than. It does not say anything what if equals the radius. So like I said, we need to check it. Okay? Now, for our last example for this set of slides, we have the following. So if we look at this, we have the series x minus 4 to the n over n 3 to the n, and from 1 up to plus infinity. Because there is a denominator n, you can only start at n equals 1. So if we expand this, we will have x minus 4 divided by 3 plus x minus 4 squared divided by 2 times 3 squared plus x minus 4 cubed divided by 3 times 3 cubed plus so on and so forth. Of course, when x equals 4, this is always convergent. So now we start for x not equal to 4. We get a limit as n approaches infinity of a sub n plus 1 over a sub n in absolute values. This is the limit as n approaches infinity. Absolute values of x minus 4 to the n plus 1 divided by n plus 1, 3 to the n plus 1 times n 3 to the n over x minus 4 to the power n. If we simplify this, we will have the limit as n approaches infinity We have the absolute value of x minus 4, so this will cancel the n here. This 3 to the n will cancel the 3 to the n here, so we will still have over 3. But these two here, they will not cancel each other, so it's just n over n plus 1. But as n approaches infinity, this will go to 1. So we will have here absolute value of x minus 4 over 3. And take note, if we want the power series to converge, we want this to be less than 1. And this is what I was saying earlier. We need absolute value of x minus a to be less than some number r. In here, x minus a in absolute value is completely isolated. But in here, we have the absolute value of x minus a. There is a denominator here. So, this one, or we have the absolute value of x minus 4 to be less than 3. Multiply 3 on both sides, you will have less than 3. So what does this mean? So radius is equal to 3. How about for the interval? Now, we have absolute value of x minus 4 less than 3. This means you got negative 3 less than x minus 4 less than positive 3. So always remember, absolute value of x less than, say, k, if and only if negative k less than x less than positive k. Here, if k is greater than 0. Going back here, we add 4 on all sides. This means that we have 1 less than x less than 7. Okay? So what does this mean? The series converges on the interval 1, 7. At the endpoints, x equals 1, we have the series n from 1 up to plus infinity of 1 minus 4 to the n over n 3 to the n. This is equal to the series n from 1 up to plus infinity of negative 3 to the n over n 3 to the n. But this one simplifies to negative 1 to the n over n from 1 up to plus infinity. Again, convergent. Now, x equals 7. We got the series n from 1 up to plus infinity of 7 minus 4 to the n over n 3 to the n. We have here series n from 1 up to plus infinity of 3 to the n over n 3 to the n. But this one here is simply the harmonic series 1 over n, which is divergent. Therefore, so here we found that r equals 3, the interval of convergence. So we include 1, but we exclude 7. So this is the interval of convergence. Okay. So this ends the discussion on this particular slide. So the next one, we will um, discuss some series representing some functions. See you in a while.